Today's lesson is going to focus on reactions of hydrocarbons. Let's go over some of the chemical properties that we're already aware of related to the three kinds of hydrocarbons that we have looked at. So alkanes tend to have low chemical reactivity because of their very strong sigma bonds. So any molecule that has just straight single bonds, any hydrocarbon, those bonds are really, really strong. And so in order to bust apart the molecule, okay, which is very different than talking about the physical property of boiling points, okay, boiling points just means moving the molecules away from each other, putting distance between the molecules. These chemical properties that we're talking about, where you actually want to break bonds within your hydrocarbon, it requires a lot of energy in order to break these sigma bonds. And so we call this activation energy, and this means it requires quite a significant input of energy to get the reaction going and to start to break these bonds initially. When we talk about molecules with pi bonds, so our alkenes and our alkynes, they have these pi bonds that circle around the sigma bonds. And because they're circling, they can react those two pi electrons away very easily. And as they circle around the sigma bond, neighboring reactant molecules can grab those circling pi bonds and bond to them. And then we know about our aromatic molecules. So the benzene molecule is the main one we're going to study. And even though the benzene molecule has pi bonds or pi electrons, remember that they are delocalized. So they're constantly circling within, very important, within the ring structure. And so they aren't exposed on the outside of the molecule like alkenes and alkynes tend to be. So benzene molecules are unique. Even though they have pi electrons, pi bonds, they are very stable. It's really, really hard to get to those pi bonds because they're in constant motion within the center of the ring. So let's go through some of these reactions of hydrocarbons that can exist, and we'll go through some examples. The first one is combustion reactions. And combustion reactions we know from grades 10 and 11 are reactions with oxygen gas. So we need to have oxygen gas, which we remember is diatomic and always exists as O2. There's two types. You can have complete combustion and you can have incomplete combustion. And this just means that the amount of oxygen that is present is different. In complete combustion, you have lots of oxygen. In incomplete combustion, you don't have enough oxygen to totally bust apart your molecule. Combustion reactions can occur with all organic molecules. This is very important. So you can combust an alkane, an alkene, an alkyne, an aromatic, and also any other organic family that exists. They can all undergo combustion reactions. And they're highly exothermic, which means that they release a lot of energy. So let's do an example of a complete combustion reaction. So I'm going to write CC on the side for complete combustion. And if we take something like a butane, so 1, 2, 3, 4, we're going to react that with oxygen. And we know from our previous courses that in a complete combustion reaction, you have lots of oxygen. It's going to totally break apart your molecule, and you end up with just two products, carbon dioxide and water. Now, water is in the liquid state, CO2 is in the gas state, oxygen is in the gas state, and then your hydrocarbon will either be gas or liquid. It all just depends on the size of it and the amount of dispersion forces that are present. Remember, with combustion reactions, you have to balance them. So when you balance a reaction like this, it's a little bit hard. It's easier to take this line diagram that we often use and convert it into its chemical formula. Then this will make it a little bit easier to balance. Take a second, balance this on your own, and then come back and check your answer. So as you go through and balance this, you're going to notice that you get an odd even situation happening when you first start to balance your molecules with those oxygen atoms. So remember that when your oxygen atoms don't balance nicely and you have an odd number on one side and an even number on the other, we just go back and we double everything. So we're going to have 2 butanes. We end up with 13 oxygens as a result. 8 carbon dioxides, and then 10 water molecules when you finally get that fully balanced. Let's do the same thing now with incomplete combustion, and we'll stick to a butane. So again, we tend to use line diagrams, but line diagrams are not helpful when we need to balance reactions like a combustion reaction. So we're just going to rewrite C4H10. This is a gas, by the way, at room temperature. We're going to react it with oxygen gas. And then when we have incomplete combustion, we don't have enough oxygen to totally break apart the molecule. So you get these other side products. So we get CO2 and H2O again, but then we also will get some carbon monoxide, which is a gas. And lastly, you're going to get pure carbon soot. So again, let's take a second and let's balance this. There's more than one way to balance a incomplete combustion reaction. So take a second, try to balance it, and then come back and just see what I've done. Okay, so in trying to balance everything, but also maintaining an even number of oxygens, just because I start with an even number over there, I'm going to start with my hydrogens, and I'm going to balance my hydrogens by putting a 5 in front. I now have an odd number of hydrogens there. I have 5, but I also have an odd number here. So I actually have an even number in total. I have 6 right there, which is good. So we're going to leave that. I need to have 4 carbons, and if I put a 2 in front here, I now have 4 carbons everywhere, and I have not adjusted my oxygens. So I had 6 oxygens from the water and the CO, plus another 2 for a total of 8, and so I need a 4. That's 4 in front there. It's possible that you maybe balanced it slightly different, and that's okay. As long as all the atoms are balanced, it doesn't matter. When you have incomplete combustion, you have less oxygen than is optimal. And what does less mean? Well, there's varying grades, varying amounts of less, okay? So maybe you're just shy of the optimal, maybe you're really shy of the optimal. And as a result, you'll always have different amounts of products produced. The next reaction we want to talk about is called a substitution reaction. So these will be new now, the next few. These substitution reactions only occur with alkanes and with aromatics. And the reason for that is because both of those groups are very, very stable. So we're not breaking any bonds, so to speak, not any carbon bonds anyway, and we're just rearranging some atoms. So now what I'm going to do is show you a couple of examples. So I'm going to take, let's take 3-methylpentane. The point here is if we have branches on these molecules, it really doesn't matter. Okay, if you have straight chains or you have branches, it won't matter. And you could substitute or react this with something mildly reactive. So not an oxygen. If you react it with an oxygen, you get a combustion reaction. But if you react it with something like chlorine gas, for example, then what's going to happen is these chlorines are going to substitute in on your organic molecule. But they can only substitute hydrogens or maybe another halogen that was there. They will not substitute for carbons, okay? You cannot break carbon bonds. But what you could do is you could take this molecule, and don't forget the branch, and maybe one of these hydrogens right here are going to come off, and you're going to substitute a chlorine in instead. And so what will happen is you get kind of like a double displacement reaction where one of these chlorines that are here, so remember they're bonded together, that one of those chlorines comes along, that's my hydrogen that was already there, and substitutes itself for that hydrogen. We could also do this with a benzene molecule. So here's an example. Again, feel free to put a branch on if you want, or if you don't, it doesn't matter. Maybe I'm now going to react it with something like hydrofluoric acid, okay, which is a reasonably reactive molecule. So what we would do here is we would substitute one of the hydrogens on my benzene ring for one of these atoms. Well, I'm not going to substitute a hydrogen for a hydrogen. That doesn't make any sense. But this fluorine will come in. Maybe he comes in right here. And I'm going to show the little hydrogen that's already there. We don't tend to show it, but I'm doing that now so that you can see that we would substitute that fluorine for the hydrogen that is there. and then the remaining 2 hydrogens will form hydrogen gas. These reactions are really hard to undergo because you're trying to break strong sigma bonds. So oftentimes we need to have catalysts with each of these reactions in order to facilitate it. An elimination reaction takes a single reactant molecule and it will split it into 2 products. So here's an example. We can take something like an alkane, and if there was something else attached to it, like a hydroxyl, so an OH group, you're going to see these soon when we get to the families of alcohols. If it had a halogen on it, even if it didn't, if it just had hydrogens, when you notice that there is nothing else being reacted with that reactant, you know this is an elimination reaction. Now, this is not an easy thing to do. So what we're going to be doing is eliminating atoms off of our molecule, and so we need a catalyst to help us do that. When you eliminate something off of the organic molecule, you cannot eliminate carbons, okay? You cannot touch the carbon-carbon bonds, but you could touch the OH, and you could take off or eliminate something else beside it, okay? So it would have to be on the carbon either on one side or the other side. Okay, doesn't matter, but I'm going to show this hydrogen that's there, and I'm going to eliminate that off as well. When that happens, H and OH creates H2O, and then we are left with a pi bond remaining where we took those atoms off. So remember, carbon always has to make 4 bonds, and so when we remove or eliminate the H and OH, it has to bond to itself in order to stabilize those valence electrons. So what happens here is you always go from a stable molecule in an elimination reaction to an unstable molecule, okay? And right here we showed you an alkane, right, that had single bonds that are stable to an alkene that is unstable. The last kind of reaction is called an addition reaction. And sometimes students are thinking, oh my gosh, look, there's 4 different kinds. Yeah, there are. It's all the same. It's just that the reactants that we use are a little bit different. So we show you an example for each one. Addition reactions sound like what the name is implying. There's going to be a reactant molecule that gets added into your structure. So the only way to add in extra atoms is to have alkene or alkyne molecules that have pi bonds, which will get broken. And those broken pi bonds will allow extra reactant molecules to be added in. So when this happens, there are no atoms left over. So let's do an example. If we have a halogenation reaction, which I think we can understand would be the addition of a halogen, let's see this in action. So let's just do a simple, we'll do a 1-butene, and we're going to add in a halogen. So remember that halogens are diatomic. I'll add in some bromine. Now, this happens without any catalysts. Remember, pi bonds are circling around the sigma, and they're very easy to break. And so what would happen is we know that bromine bonds to itself like this. And like a magnet, these bromine atoms are attracted to both carbons that are being circled by the pi bond. The pi bond gets broken, and then your bromine atoms get added in to the carbons that held the pi bond. So let's see another example where we have hydrogenation. So if we have a hydrogenation reaction, like the name implies, we're going to be adding in hydrogen. So let's do this now with let's do an alkene. Okay, so I'm going to do, an alkyne. And I'll throw a branch on, but branches they don't matter. Okay, so you can have as many branches as you want, it doesn't matter. This is all about the pi bonds. So we're going to add in hydrogen into our molecule. But the thing is that one hydrogen is going to break one pi bond, one hydrogen molecule. You need a second one because you got to break 2 of them. So we actually have to balance this, and we need 2 sets of hydrogens here. So like a magnet, these reactant molecules will be attracted to the pi bond. Make sure that you put your branch back in. And even though we don't tend to show hydrogens, we're going to show that, one molecule of hydrogen broke the top pi bond. Another molecule of hydrogen broke the bottom pi bond. And we always write that in because we want to make sure that, I understand that you know what is happening in these reactions of these molecules. Now let's look at an example of hydration. So if we're doing an example of hydration, this would be adding water. And remember that water has a structure of H2O, but water behaves like this, H and OH, whenever you're reacting it in an actual chemical reaction. So let's do an example of a hydration. So I'm going to take now a cyclohexene, and I'm going to add water to it. So we tend to show the water molecule like H2O, but we have to remember that it behaves like that. So what will happen is one of these hydrogens are going to go and break the pi bond and get added in here. The OH will get added in to the other side. So when we show this afterwards, don't show the pi bond. It's been broken. And you're going to have a hydrogen at the top, and you're going to have an OH at the bottom. Okay, so this is now making a family that's called an alcohol, and that OH is being very specific to it. Sometimes when we are adding in a molecule that has one hydrogen and something different bonded to it, we have to be aware of Markovnikov's rule. And you have this listed at the bottom of your note. Okay, so this is a very, very, very important rule. And Markovnikov's rule actually doesn't apply to that first reaction that I did here, but it would apply in a structure like this. Okay, so if I just take one butene and I add water to it, now the placement of my hydrogen and the placement of my OH is going to be very specific. And so Markovnikov's rule states that the rich gets richer, and whichever carbon has more hydrogens is going to take the hydrogen out of that reactant molecule. So we're just going to show here, we know carbons make 4 bonds. So at this end carbon here, he would have 2 hydrogens already present. And then right here, he would only have 1 hydrogen present because he already has 3 bonds taken up. So the rich gets richer. What will happen here is as we break that pi bond, the extra hydrogen will go to the carbon that already has more hydrogens, and the OH will go to the carbon that has less. The same idea will apply to hydrohalogenation. So this is the addition of a hydrogen halide. And these would be molecules like, HCl. It's a hydrogen and a halogen, right? HCl, HF, HBr, and such. And so the same idea can apply. So, if the rich gets richer, you have to be mindful of that. Sometimes though, like in this example, the number of hydrogens around the pi bond stays the same. So then you don't really worry about Markovnikov's rule. But let's do one where we would. So we're going to see, let's put my pi bond here, and then let me put a branch in there. And when I put that branch in, now the number of hydrogens around those pi molecule or pi bond is going to be different. I actually have no hydrogens right here in that structure. And over on this structure, I have 1 hydrogen remaining. If I react this with HF, let's say, then the rich is going to get richer. This hydrogen is going to break the pi bond and get added in there, and the fluorine will go to the other bonding site because there are no hydrogens present. So we'll just show that here. Don't forget your branch, you got to put it in. And then we'll show that we're going to put the hydrogen there and the fluorine there. So the reactions some of them are brand new. Be mindful of some details, and for sure be mindful of Markovnikov's rule when you're dealing with reactant molecules that have a hydrogen and something else bonded to it.